Alright students, so in this video we're going to be going over molecular orbital theory using images from WebMO of the molecular orbitals calculated for various diatomic molecules. And we're also going to try to build energy diagrams, so thinking about what our energy diagram for molecular orbitals will look like. So the first thing I want you to do is go to WebMO, log in right on the chem server to WebMO, and you will have 3 calculations that I have copied to your account. All 3 are molecular orbital calculations. One is for nitrogen, one is for fluorine, and one is for oxygen. Open up the nitrogen one so that you can see it side by side. Remember that if you scroll to the bottom of the results, the very last table of the results is the molecular orbital or molecular orbitals and their energies. And you can click the magnifying glass at any point to see a molecular orbital. All right, so we're going to start with diatomic nitrogen. If we think about its Lewis dot structure, we see that it has a triple bond between the 2 nitrogens. And if we draw an energy diagram where we think about nitrogen 1 and nitrogen 2, we can think about their individual atomic energy diagrams. They will each have 1s, 2s, and 2p orbitals that have electrons in them. There's a pretty big gap between the 1s and 2s in energy, so this is certainly not drawn to scale. And we can put in the electrons, the proper electron configuration. There should be 2 electrons in the 1s, 2 electrons in the 2s, and 3 unpaired electrons in the 2p orbitals for each of the atomic nitrogens. But what does the molecular orbital diagram look like? Let's find out. So the first thing I want you to do is we're going to look at the energy molecular orbital that has an energy of negative 15.61 AU, and there's another one that has negative 15.609 AU. So click on the first one, the negative 15.61 atomic units, and let's look at what that looks like. So give you a second, pause the video, open up that molecular orbital for nitrogen, that very first one. Okay, so you should see that these look fairly atomic. So if you look at the very first one, you should see the image on the left where you have 2 blue circles, one centered on each of the nitrogen nuclei. But if we go to the second one, we have 1 blue and 1 red. And we'll notice that we have a node in the middle. Interesting. So both of these look fairly atomic. The wave functions themselves are actually completely centered on the nuclei themselves. There's nothing in between. So these aren't really molecular orbitals, they're atomic orbitals or atomic-like orbitals, which we would expect because the 1s is in the core of the nitrogen. It's not a valence electron. So think back to general chemistry. We told you that the important part of the electron configuration was the valence shell or the outer shell. And so here we expect that these will be fairly atomic, and certainly they do look fairly atomic. But again, keep in mind that you do get a node going from the first to the second. But these are very, very nearly degenerate, and they're essentially 1s. And so another term that we're going to introduce is gerade, which is German for even function or even. And so if we draw a line in between the 2 nitrogens perpendicular to the axis, and we say that that's 0, right? The center of that line, we could think about drawing a full coordinate center and a full coordinate XYZ coordinate system and putting the 0 right in the middle of the bond. And that would be 0, 0, 0, which we will need to do later, but right now we don't need to do that. And we can see that the left-hand side and the right-hand side, or the positive and the negative side here across the z-axis or the bonding axis, are even, right? So negative x is equal to positive x as far as the wave function. And so this first one is a 1s gerade. Our second one, however, are just ever so slightly higher in energy, the one that has the node. If we look at the left side versus the right side, or the negative side versus the positive z, we see that this is an odd function. So we're going to introduce another German word, which is ungerade. ungerade is a German word meaning odd or odd function. And we see that this is indeed an odd function. So we will signify this as 1s ungerade. Sometimes you will see in your book that these are noted as sigmas, but technically they are atomic s orbitals. All right, so now let's look at the next set of orbitals, the next higher one up. So go ahead and click on the third orbital, and you'll see that it's at negative 1.52 atomic units, or AU. What does that one look like? So click the negative 1.52 orbital, see what it looks like. Pause the video if you need, rotate it around. So my drawing of this is this one, which is cylindrically symmetric. So that means if you were to stand this on its end, right? So maybe you were to stack the two nitrogens and look down the actual bond from one nitrogen to the next, and you were to rotate it in a circle, counterclockwise or clockwise, the whole thing would be the same. It's symmetric as if it were wrapped around the z-axis or the bonding axis. That's what we mean by cylindrically symmetric. And all sigma type bonds are cylindrically symmetric. So this is a sigma bond. And there's bonding or wave function. There's wave function, and thus there will be probability between the two nuclei. So this is a bonding orbital. So this is a sigma. Sometimes it'll be denoted sigma 2s because it comes from the 2s. And if we draw our line down the middle to think about whether or not this is an even function or odd function, whether we think about the z-axis, the x direction, or the y direction here, it's even in all three directions. So it is a net even or gerade function. So we would signify that by calling it sigma g or sigma sub g. So we can label this molecular orbital that occurs at negative 1.52 AU as a sigma g orbital. All right, well, let's look at the next one. So go ahead and click on the negative 0.78. And you should get something that looks something like this. So feel free to pause the video, rotate your molecule around in WebMO. You'll notice that this is also cylindrically symmetric. Again, if we rotate it almost like the bond was a rolling pen and we're rolling it out, it's even all the way around. It's the same all the way around. So where it's red, it's always red all the way around the z-axis. And where it's blue, it's always blue. And where there's a node, there's always a node. So this is cylindrically symmetric, so it's still a sigma. If we draw a line down the middle, we see there's a node in between the two nitrogens, which means there's no wave function or no probability of finding an electron between the two nuclei, which means this is an anti-bonding orbital. So we're going to signify anti-bonding by putting an asterisk next to the orbital type. So this is a sigma star. And if we look across the z-axis, we'll see that when we have a negative z and a positive z, they are opposite in sign. The wave function is opposite in sign. So it is ungerade. If we were to look in the x direction or the y direction, we would see that it's even. But along the z-axis, it is odd, and even times odd is going to give us an odd function. So this is indeed sigma ungerade star. So we can label the negative 0.78 with a sigma ungerade star. So let's go look at the next orbitals. So raise this one. The next two actually appear at the negative 0.62 atomic units. And you'll see that you have two different orbitals that appear at the same energy. So they are degenerate. Just like our 1s were nearly degenerate, these are truly degenerate. So I want you to click on those and see if you can figure out what the difference is between the two of them. All right, so I've drawn one of them. So you have your two nitrogens. You have a long sort of red lobe on one side, and 180 degrees from that you have a blue lobe of wave function. So one side is positive, the other side is negative. There's no wave function actually along the z-axis. So this is not cylindrically symmetric, right? If we were to roll this like a rolling pin, it'd go red, blue, red, blue, red, blue, red, blue as we were to roll it out, as opposed to staying the same color all the way around. So this is not cylindrically symmetric. Another way to look at this is it has a nodal plane that cuts parallel to the bonding axis, right? So it encompasses the bonding axis into the planal node, which means it is a pi orbital. So this is going to be a pi-type orbital. And if we look at even versus odd, along the z-axis, it's even, right? So if we go from one side, one nitrogen to the other, we stay even, or we stay odd, or we stay zero. But if we go in the x direction, in this case, the way this one is drawn, if x is along where the red line is, then it's odd, and the y direction would be even. Or if we were to look at the other degenerate orbital, this would be 90 degrees offset, so it'd be even in x and odd in y. Right? So either way, so the difference between these two degenerate orbitals is they're rotated 90 degrees in the xy plane. All right, so because we have even times odd, that makes this an odd function, or an Ungerada function. So this is a pi Ungerada. If we think about where the electron density is, it is between the two nitrogens. Technically, it's slightly above and below where the nuclei lie, but it is still in the space in between, and so this is a bonding orbital. All right, so we can label these two degenerate orbitals that occur at negative 0.62 atomic units as pi Ungerada. So now I want you to go look at the next one, which occurs at negative 0.616 AU, so very, very close in energy. Very, very close in energy, almost degenerate to your pi Ungerada, but a little bit higher in energy. So go look at that one. You should see that you have something like this, where you have two red lobes or negative lobes that are centered on the nitrogens, and then you have a blue lobe in between the two nitrogens. And so we think about rolling this out like a rolling pin. The middle part will stay blue all the way around, and both of the ends will stay red all the way around. And so this is cylindrically symmetric. Another way to look at that is there's no planal node that encompasses the bonding axis. And so this is cylindrically symmetric, so it's a sigma type bond, right? Sigma, or single bond. And we have two nodes, both which cut into the bonding axis, the z-axis. However, we still have a significant amount of wave function or probability that sits directly in between the two nuclei. So this is still a bonding orbital. So sorry, I think I have a, let me get rid of that. Well, maybe, nope. There we go. I had an asterisk there, I shouldn't have. So this is a bonding orbital, so this is a sigma, not a sigma star. Sorry about that. And if we look at whether it's even or odd, so we can see that from left to right. So cylindrically symmetric means that the x and y will always be even functions for sigma. But if we look along the z-axis here, it is also even, right? It's like a mirror across the center. So this is a sigma Gerada orbital, so we can label that up there as sigma Gerada. So now I want you to find the next orbital or orbitals. So the next one in energy should be, again, doubly degenerate, and it should be at positive 0.186 atomic units. It's positive because it is not filled. So this is the LUMO, or the lowest unoccupied molecular orbital. And so what do those two orbitals look like? What's the difference between them? So when you plot them, you should see that you have sort of this weird four-leaf clover thing going on around the nitrogen. So each nitrogen has both a blue and a red lobe. And there's a node actually cutting along the z-axis, or encompassing the bonding axis. And because we have that one node that encompasses the z-axis, or the bonding axis, we know that this is a pi-type orbital. However, that's not our only node. We have another node cutting straight through the middle, and that additional node prevents there from being significant wave function or probability directly between the two nuclei, which means this is an anti-bonding orbital. So this is a pi star or a pi anti-bonding orbital. Now if we look across the axes, it's going to be odd in x, odd in y, and so this is actually going to be an even function. And this is going to be even in z because there's nothing along the z-axis in this case. So it's odd in x and odd in y, which makes it an even function overall. So this is a pi Gerada star or pi Gerada antibonding orbital. So we can go ahead and label those as well. And again, if we look at the two different ones, what you should notice is that they're 90 degrees apart. You might also have noticed that Webb and Mohs switched colors from red and blue to yellow-green. That's to make sure that you realize that you're now looking at unfilled orbitals. So the green and the yellow also represent positive and negative, just like red and blue. All right, so let's look at our next orbital, which occurs at positive 0.762 atomic units. Again, it's unfilled. What does this one look like? So you should get something that looks like this. So we've got several nodes going on. Is this one cylindrically symmetric? So if we were to roll this like a rolling pin across the counter, would the part that's red stay red as you rolled it? Would the parts that are blue stay blue as you roll them? Yes, so this is cylindrically symmetric. It is a sigma bond. So it's a sigma molecular orbital, or a sigma bond. We have 3 nodes that cut through the space in between the two nitrogens that cut perpendicular to the bonding axis. And notice that one of those nodes is directly in the middle, which is going to mean that there's no probability of there being a significant amount of wave function in the middle of the bond, which makes this an anti-bonding orbital. All right, so if we were to look left to right, again, this is cylindrically symmetric. It's sigma, so we only have to think about the z-axis because x and y will be even. If we think about z, we'll notice that it's odd. The colors go in the opposite order as we go left versus right from the center. So that makes this an odd function. So this is a sigma Ungerada star or sigma Ungerada anti-bonding orbital. And so we can go ahead and label that one. And we can fill all of our electrons. So each of our nitrogen atoms contributes 7 electrons. And so we should have 14 total electrons when we fill. So we'll see that both of our 1s's get filled. Remember, these were our basically atomic 1s looking orbitals. And we'll see that our sigma Gerada and our first sigma Ungerada get filled. Our pi Ungeradas are all full, and our sigma Gerada is filled. So what is the bonding order of, or bond order of this molecule of nitrogen? Well, we know from our Lewis dot structure it should be a triple bond. So let's see if that holds true with molecular orbital theory. So our bond order is 1/2 the number of electrons in bonding molecular orbitals minus the number of electrons in anti-bonding molecular orbitals. So I'll let you do that math for a second. You should get 1/2 times 6 or 3, because you'll notice that in the 1s orbitals you have just as many bonding as an anti-bonding, or we could really call both of those non-bonding as opposed to bonding or anti-bonding. They're non-bonding because they're basically still atomic orbitals. There's no bond present, so they have 0 contribution. If we go to where our 2s splits into sigma Gerada and sigma Ungerada, remember that there are 2 electrons in each, so 2 electrons bonded, 2 electrons anti-bonded. Those will also cancel out, so we only have to consider the electrons coming from the orbitals formed by the combination of 2p atomic orbitals. And we'll notice that we have 6 in bonding orbitals and 0 in anti-bonding orbitals. So 1/2 times 6 gives us a triple bond, which is exactly what our Lewis dot structure also predicts. So some general trends to note is that you get 1 bonding molecular orbital and 1 anti-bonding molecular orbital for every combination of atomic orbitals, which is something that we also said when we were looking at linear combinations of atomic orbitals. Atomic orbitals of similar energy and similar geometry are the ones which will combine to form molecular orbitals with one another. We'll talk more about geometry later. And for like molecular orbital types, you gain a perpendicular node to the z-axis as you go up in energy. So if we look at our atomic 1s, our non-bonding orbitals, the first one had no node because both of the lobes were blue, even though there was space between them. But the second one of the lobes was flipped red, indicating a node. And if we look at our sigma Gerada, our lowest one, our sigma Gerada, had, from the 2s orbital, had no nodes. Sigma Ungerada star, which was our antibonding, had one node. But then the sigma Gerada that was bonding from our 2p orbitals, all of a sudden it was bonding, but it had two nodes. And the one above that was antibonding, the last one we looked at, was also sigma, but it had three nodes. If we look at sort of the same type of orbitals, we'll notice this trend that as we go up, and we can see the same trend will happen with the pi's. The pi Ungerada, both of those had the node that makes them a pi orbital, but no additional node. When we went to pi Gerada star, there was an additional node. So we'll gain additional nodes for like orbitals as we go up in energy. All right, so your next part of this activity is going to involve looking at the fluorine and the oxygen Webb-MO calculations that I've shared with you. After you've done that, we'll move on to one other thing with these molecular orbitals for today.